Well, hello, my San Francisco Theosophical Lodge buddies. This is Jeff Curtis coming to you again from the Sierra foothills, and I wish you all a pleasant winter time. I hope everything is um, good for you at your end. I'm enjoying wintertime, sort of, up here now. I'm having to burn fires and do a lot of work to stay warm in the mountains. Excuse me, I'm just checking my messages here to see if everything's okay. Um, I hope I'm coming through uh, to you all right now. At least from what the screen is showing me, I am. So I'll keep going here unless I get warned otherwise. Um, so what I wanted to do tonight is spend a little while talking to you one more notch into the nature of quantum objects and the ways in which we describe and understand them, how they are behaving, what the mysteries are. I'll point out things we understand and can calculate, and then things that are still up for debate and signs that we don't really know the whole picture yet. Um, Bits and pieces of this have been discussed before. Uh, with you folks, but I'm going to take a slightly different tack tonight. I'm going to actually show you some numbers that have interesting relevance both to the history of the development of quantum mechanics as a science and to illuminate one of the puzzles and surprises that we're just kind of left having to deal with um, in the in our struggle to wrap our heads around what quantum mechanics is telling us. So humans encountered quantum mechanical phenomena at a certain point in history when our technology reached subtle levels of energy. So we could measure small amounts of energy in, we could manipulate objects at a very fine level. That's what it took in order for quantum properties to become obvious and apparent and present themselves as something we were going to have to deal with. Um, what I opened up with last time, what we discussed a part of, was the wave-particle duality of light. You'll recall that scientists in the 1800s had done a lot of experiments showing that light had a wave-like nature. You could refract light, you could diffract light. I'll come back to that word again in a little while. There were manifold ways in which light was showing itself to be a wave-like phenomenon. But then it was in the early 1900s, starting in a sense with the work of Planck, but then really getting ground with Einstein's interpretations of the photoelectric effect, that there came to be modern and inescapable evidence for the quantum nature of light. The fact that light seems to be coming to us in little pieces. It's not a continuous thing. Yeah, it has wave-like properties. We can measure those, and they're reproducible. But there's more to the story than that. So it's corpuscles. Now, Isaac Newton had intuited this somehow, way back in the 1700s. There was a debate where Newton held up the notion that light was not a continuous wave-like phenomenon, but it had a particle-like nature. A sign of what a genius he was. He couldn't explain it. He couldn't convince many other people, but the idea was there. He had it somehow. We don't, or at least I don't really know how he had it, but he did. Well, anyway, the photoelectric effect I've now explained a number of times, so I'm going to go very quickly through it. The photoelectric effect, which was essentially a body of data laying around, that it took Einstein to synthesize in his head and grasp what it meant, is simply this. If you have a metal target and you shine light on that target, it will eject electrons if the light has a short enough wavelength. In other words, does it carry enough energy? So energy of light is equal to Planck's constant times frequency. I'm going to put up an equation here to remind you of that. So energy of a photon, Planck's constant times frequency. Frequency is cycles per second of a light beam. There's another level of refinement, though, where I'm going to rewrite that a little bit. And you can look at it this way. Excuse me, I know this is annoying to watch, but that upper line, energy equals Planck's constant times frequency, also can be rewritten as Planck's constant times speed of light over its wavelength, lambda. That Planck's constant was a huge intellectual leap, and it was effectuated by Max Planck in the late 1800s. He was actually studying the way in which light comes off of heated objects, so-called black body radiation. He discovered really that light had to be quantized even before the photoelectric effect. He linked emission of light to oscillators in a body, like a red-hot coal or something that's giving off light. He was able to derive that constant, but he didn't quite derive the entire whole picture of it. That was Einstein. So Einstein discovered as long as the light hitting this piece of metal has enough energy, it'll blow electrons out. Furthermore, it became clear that once the threshold energy was met, meaning the light had to be of a certain wavelength or shorter, because the energy of light goes up as the wavelength gets longer. So if the light waves are too long, they won't have enough energy when they hit this target. As long as you meet the threshold, then what they discovered is that the amount of ejected electrons, which they could count with the detectors they had back then, depended on the brightness of the light. That was the link. That was the crucial insight. Brightness of light, they could fairly easily see, well, that's probably the amount of light. What's that? Well, maybe it's the number of light particles per second. And you go to a brighter light, you're getting more particles per second. And, that's when we see more electrons per second being ejected. But if you go to too long of a wavelength, say you're using red light, no brightness of red light is going to eject electrons. So there's this energy threshold. That ends up being a huge hint into the construction of matter at the level of atoms and molecules, which we'll return to eventually, but I'm not going to dwell on that right now. I just want to get to this wave-particle duality thing. All right, let's push this a little farther. I'm going to show you another equation that you've seen and that you have been aware of for maybe a long time. You know that Albert Einstein, in his studies of special relativity, came up with E equals mc squared, where we're talking about now relativistic mass energy of anything, and we can apply that even to photons. So that's the mass times the speed of light squared. I'm skipping some steps here to make this simplest as I can get it. All right, well, that's interesting. Now, let's just do something that you may remember having done in high school. We have two equations defining energy, the first one at the top and then the one down from there. Two expressions for energy. Let's equate them in a line. So now the line you see on this page says energy equals mc squared is also equal to Planck's constant times frequency, and it's also equal to Planck's constant times the speed of light divided by the wavelength of the light. This is simply rewriting frequency. So the frequency of any wave-like phenomenon is equal to its speed of propagation divided by its frequency. How fast is it going up and down? So this is a fundamental equation out of wave behavior that is well confronted by anybody who's had a high school physics class. Okay, well, we can rewrite that then. We get to this equation that you see now. Mass times speed of light equals Planck's constant divided by wavelength. And we can at least posit that this seems to work for photons. certainly suggested by equations that have been verified and multiply tested. Well, it was in about 1922 to 23 to 24, a very interesting guy named Louis de Broglie. He was I think, I'm pretty sure French nobleman. He's actually called Count de Broglie. He was one of the interesting class of very wealthy um, European gentleman, philosopher, experimenter types, and he was also very smart. So he was able to educate himself. I mean, I think he went to university, but he was also just a ferocious self-educator and a deep thinker. And de Broglie looked at that equation, and he was picking up on. He knew about the wave-particle duality thing had been established by Einstein, and people were really wrestling with the range of phenomena they were seeing. Part of this is because at that time, around the turn of the century, was when we developed the ability to manipulate beams of charged particles like electrons or protons. The cathode ray tube was invented back then. And this began to show some strange effects that were not always real reproducible, but nonetheless a picture was emerging that this idea of a wave-particle interplay or duality might be bigger than photons. And de Broglie was the guy who sort of got there first. And what he did was he reasoned from the first equation there, that one, mass times speed of light equal Planck's constant over wavelength. And he said, what if it's more general than that? What if we could plug any velocity v in for c and think about the wavelength of particles in general, like, for example, electrons? And he developed this equation that lambda of whatever kind of particle is equal to Planck's constant divided by the mass of that particle and divided by its velocity. And that would be now not the velocity speed of light, but any general velocity from very slow to velocities approaching the speed of light. And that was his huge intuitive leap made by analogy, essentially. And it only took 2 years for experimental evidence to accumulate. There was a classic experiment by Davison and Germer in 1925, where they had learned how to produce and control beams of electrons in their lab, and they could energy select them so that this beam of electrons would all have about the same speed. Well, what we're doing right now is we're coming up with an equivalence between or a relationship between the kinetic energy of electrons, their energy of motion, and their wavelength. And by both planning and good luck, and it turns out there was an element of luck involved, but through both of those things, they impinged a beam of what we would call monochromatic, all the same wavelength electrons, onto a metal target. And it turned out that the lattice spacing between atoms in that metal target was of the right dimension to allow diffraction to be observed, now not of light, not of photons, but diffraction of particles, quantum particles, the ones we call electrons. That rocked the world because it really put us off to the races in terms of very rapid development of quantum mechanics, which came soon after that. Now, I want to drop back a minute. I've now used the word diffraction a couple times. So, what's that? Okay. Diffraction is a key property of wave-like phenomena. So if something is manifesting and moving with an associated wavelength, we will observe a few basic phenomena, wave-like phenomena. These would include refraction, diffraction, and interference. The one we're focusing on right now is called diffraction. And so I'm going to illustrate for you here sort of a crude illustration of what that is. Imagine, for example, light is a vibrating electromagnetic wave packet propagating to the right. But imagine light waves or any kind of waves hitting a barrier. So those vertical lines, the 4 vertical lines, are just representing the wave front of some wave-like phenomenon impinging upon a barrier. If you let that happen, they will go through the barrier if the wavelengths are close to or smaller than the size of the slit. And if you collect those things on a screen, like a photographic plate, you'll get this pattern of lumps. You get kind of a big lump in line with where the slit is. That's a slit between 2 barriers. That's how we're looking down on top of that. That could be, for example, a microscope slide that's been coated with gold and had a single, very thin line etched in it, up and down. So that's one way of creating a slit of correct dimensions to elicit diffraction. So the key, the constraint, the condition for seeing diffraction like this is that the slit width has to be of order of the same size as the wavelength of the light, or a little bigger. It has to be tuned. As long as you get it tuned, then you'll see this diffraction. And it turns out that what's going on here at a deeper level is that the corners or the edges of the slit are essentially acting as sources, point sources. That's a way to mathematically model this. And the distance between the lumps here in this is called a diffraction pattern. And the spacing of those lumps is readily calculable if you just know the distance from the slit to the detector target and the wavelength of the particle and the width of the slit, and you can compute the size of that, the periodicity in that diffraction pattern. So that was huge, and it sparked a explosion of experimentation. Now people started learning how to make beams of protons, beams of neutrons, even more recently beams of molecules. It kicked off a huge revolution in gas phase manipulations of atoms and molecules, and sometimes impinging these beams on each other and looking at how they react and how the products scatter off. It's a whole big interesting area of science. But what I want to get to and point out is that one of the first things people did was they extensively tested that de Broglie equation. Okay, so let's think about an example. Suppose we have a beam of electrons, and the electrons are going at 100 meters per second, the way I've written it there near the top of the page. And we plug those values into the de Broglie relationship. We say, well, okay, the wavelength of those electrons would be lambda, equal Planck's constant, divided by the mass of the electrons, divided by their velocity. So velocity is 100 meters a second. The Planck's constant is what I've written in there, 6.63 times 10 to the minus 34th. Units are joule seconds. And we're going to divide that by 100 meters a second, and we're going to divide it by the mass of an electron, which people had figured out how to measure the mass of an electron, which is impressive, because you look at that, it's a small thing, 9.1 times 10 to the minus 31 kilograms. How'd they do that? Well, it's a long story. It involves shooting electrons, which had a known charge on them, of a known velocity into magnetic fields and watching how they curved. That would be a long song and dance. But anyway, in this particular case, what you can compute is that for that beam of electrons, the electron wavelength is 7.3 times 10 to the minus 6 meters. Another way of saying that would be 7 microns. And we can do that. We can make slits that are that width and diffract stuff through there and study the diffraction pattern that gets made, and it all worked out. It turned out that de Broglie had the right intuition from his understanding of relativity and his willingness to make a big intuitive leap and say, well, this thing we kind of understand over here, maybe it applies over here, at least with a similar mathematical form. Let's write those equations out and check. And it worked. Okay, so let's go to another example. Suppose we contemplate only slightly more difficult experiment at the time, which is a beam of protons. Proton is much more massive. So now protons traveling at 100 meters a second, we can compute their wavelength, and we got the Planck constant in the numerator, and the denominator now has a 1.63 times 10 to the minus 27th rather than what we had before, 10 to the minus 31st. Plug through that, now you get a wavelength for that proton traveling the same speed as before of only 4 times 10 to the minus 9th meters. So that's 4 nanometers. That's 1,000-ish times, or going on 2,000 times smaller than for the electron. And the reason is because of the larger mass of the proton. I'm not 100% sure whether, at what point in history people figured out how to make slits of that size, but you can certainly find lattice constants of that size, and they were able to soon validate that this worked for beams of protons, although I'm not 100% sure on the speed they were using for the photons to get them into the right wavelength size range in order to diffract off of the targets they had to use back then. Okay, fine, works. Now let's go to another familiar object that we kind of all know about. Let's think about a golf ball going 100 meters a second. So, golf ball at 100 meters a second. I'm going to just kind of take a guess and say a golf ball weighs about 1/10 of a kilogram. That would be 100 grams. Now, the wavelength of our quantum golf ball is 6.63 times 10 to the minus 34th divided by 0.1 and divided by 100. That gets us an answer of 6.63 times 10 to the minus 35th meters. That's really small. 10 to the minus 35th meters, turns out that's way down at something we call the Planck scale, sort of the minimal, definable, explorable units of space-time itself. Wait a minute, a golf ball's about this big. How could it, that's a couple centimeters across. How could it have a quantum wavelength of 10 to the minus 34th meters? We can do another calculation. If you just do the computation for an average person, say a 60 kilogram human walking along at a couple meters a second, you'll find out that the person's wavelength walking 2 meters a second is 5 times 10 to the minus 36 meters. That's even smaller. What the heck does that mean? You would certainly never be able to build something to elicit a diffraction pattern because we can't manipulate matter down at size scales like that. We're doing really good to manipulate matter down at the size scale of 10 to the minus 10th. What this says is the theory's blowing up. It's as good as the quantum theory seemed to be working for a while there, it's falling apart. Or you're making a mistake. It's a non sequitur of some kind that your theory is returning to you when you push it outside of its limits of applicability. This is an interesting juncture. From a scientist's point of view, it says, you're going to have to go back to the drawing boards if you want to really come up with a notion of quantum wavelengths for macroscopic objects. In fact, probably, given what your equations are doing, you just shouldn't do that. It probably doesn't make any sense. It's a non sequitur. Physicists use a particularly nice word for situations like this where they'll say that, that answer for that wavelength is unphysical. And yeah, that's what it is. Let me take a minute here and say something. It's going to sound like a crotchety old wet blanket science guy. If somebody tries to sell you quantum dish soap or tell you something about what they can see in your aura about your quantum wavelength, you might want to consider that a red flag. Um, the word quantum gets used in a lot of really hacky ways by people who are trying to add fairy dust to things. And you now understand, like you may never have before, why you don't want to let people tell you things about your quantum wave function or your quantum wavelength, because it's a non sequitur for macroscopic objects. Now, I hope I haven't upset anybody with that, and I would recommend caution going out and trying to explain this to your friends who bought the quantum dish soap. But yeah, it's a thing. All right. Now, what else do I want to bring up here? Wave functions. Okay, I've said that word a couple times now. I don't really have time to develop that concept in great detail, but suffice it to say that from these insights, understanding that matter down at the small particulate size of atoms and molecules at least is behaving reproducibly, measurably, and in a manipulable fashion like waves, the science of quantum mechanics took off. Erwin Schrödinger came up with the Schrödinger wave equation. Werner Heisenberg came up with a mathematically equivalent treatment called matrix mechanics. And a giant field of understanding of the nature of atomic and molecular physics just presented itself. And then not too long after that, nuclear physics, because the little particles down in the nucleus, we call them the nucleons, so the neutrons, protons that are comprising the nucleus of an atom, and then the electrons are distributed around that in smeared out wave function formulae. Wave functions were first computed and understood in the context of electrons, as those electrons distributed themselves around a positively charged nucleus. But it wasn't too long before people figured out how to dive the next level in and interrogate the nucleons and see how they were behaving. And we just went through a thing where we computed the wavelength of a proton. That's one of the nucleons. Well, the nucleons turn out to be composed of, among other things, quarks. In fact, primarily quarks. Those quarks, they're weird little dudes that live inside the protons and neutrons. They're wavicles too. They exist in a wave-particle duality, and there's ways to probe that and work with that and understand it. And mathematically, what ends up being forced upon us once we invented the Schrödinger wave equation, which I'll try to hit in a little bit more detail next time, is that the wave function that we use to describe systems at the quantum level mathematically as vibrating whatevers in space and time necessarily include what are called imaginary numbers, or sometimes you'll hear this called complex numbers. So an imaginary number is just a regular number multiplied by the symbol I, where I stands for the small or lowercase I. That stands for square root of -1. If you think back to your high school algebra courses, you might realize that's hard to figure out. What's the square root of -1? Oops, I just got a notice. Okay. Square root of negative 1, I mean, something multiplied times itself is equal to minus 1. Well, you have to break out of the normal thinking about numbers. And you just have to accept the fact that there are some numbers that will have a real component, a positive number, and then plus or minus an imaginary component, which is a component multiplied by the square root of 1. And you can do all kinds of mathematics with those. And in fact, you have to use those to do the mathematics that will describe quantum wave functions. But the weird thing is, we can never directly touch those things. In order to see phenomena predicted by those wave functions, we have to let them interact either with themselves or with our measuring apparatus in such a way that what we end up measuring are probabilities of outcomes that are computable only from squaring those wave functions. Because when you square an imaginary number, suppose you've got square root of negative 1 times 3. If you square that, it becomes real. It becomes minus 9. Because square root of negative 1 times square root of negative 1 gives you negative 1. And I times 3, quantity squared, gives you minus 9. So this is kind of a weird math system that you may never have worked with before, but it's a real thing, and I'll try to make that a little bit more real next time we talk. You've heard me now mention these wonderful books by Ruth Kastner, who has done a lot to popularize the version of quantum mechanics that we're going to be getting to eventually somewhere in this series of talks. She has this fun book called Adventures in Quantum Land. And she sort of, she does a really nice job of getting us to think of this realm of wave functions, complex numbers, and stuff that mathematically is hard to deal with, but it seems to be necessary. She makes recourse to the image of iceberg and talks about how our perceived, measured, interacted with reality is the top part of that iceberg, whereas the full quantum nature, the full quantum reality of it is down there beneath the surface, someplace that we can't directly see and touch, but it's still there. Another interesting way that she tries to sketch out how to think about this, these conundra that we hit, is using the idea of Plato's cave. And some of you may have already learned about that. It was a very ancient idea. Greek philosophers were really good at sitting around thinking about what's the nature of reality and perceived reality. And they thought about it hard enough to realize that what we perceive is probably not the whole story. And what came about was the notion of Plato's cave. And the full story, I believe it involves a group of prisoners who were captured and they're forced to live in a cave, and all they can look at is the back of the cave, where they see shadows playing on the wall of people who are outside the cave, and light is shining through, and they're able to see stuff on the wall, and sometimes there seems to be a correlation, maybe even a cause and effect relationship between different of these shadowy things you see on the wall. But no matter how long you looked at the projections of shadows on the wall, you're probably never going to make the intuitive leap to the full nature of reality back there outside the cave, where there's people holding up their hands in front of the light doing this. But we try anyway. And Louis de Broglie kind of did it. What you saw here is someone with a big enough mind, maybe almost an Einstein level mind, making the leap. Oh, wave particle duality in light, maybe it's more general. Maybe we could test for that. That's a little bit like figuring out something about the reality back there just from looking at the shadows on the wall in Plato's cave. So Yeah, impressive, kind of beautiful and important. There's another interesting metaphor for all this, which Ruth Kastner goes into and brings up in her books, uh, which is Edwin Abbott's magnificent old book called Flatland. And I don't think I'll go into that right now, but Flatland, it's really a trippy book to read, written in old Victorian English ethos and prejudices, and in many ways it's kind of sociologically horrifying. But it's the one of the idea of there's beings living in a flat plane. What would happen? How puzzled would they be if a three-dimensional being came along and interacted with them? How would they explain it? How would they experience it? How would they explain it? All three of these have direct bearing on the mysteries that we're presented with when we decide to get quantum about things. So with that, I think I'll bring it to a close, and I wish all of you a very lovely Merry Christmas and a Happy New Year, and I'll see you sometime in early 2024. Okay, good night. Jeff out.